So guys, we were doing the Fourier transform. Okay, so why we moved towards another domain, which is the Fourier domain. We discussed this last time as well, that one of the motive behind transformation is the filtering operation. Okay, that makes the filtering easier as compared to time domain. Okay, this is one of the things. The other thing is the sampling. We discussed the sampling. We said that we sample the signal, right? But how many samples are needed? So the Fourier transform gives us this information. Okay, and we will see today. So there are two things. Okay, one is the filtering. Previously we were doing the filtering using convolution, right? And we make a filter, convolve with the image, right? So in other words, we want to move towards the Fourier transform to make that filtering operation, which is the convolution actually, as a simple multiplication operation, which will be easier for us. This is the one advantage. The second advantage is the sampling. Okay, so we will discuss these two as the transformation. Okay, I give this example that let's say I want to filter this image. We have two patterns. One is the image, which is smoother. Okay, so it's like a low frequency. Okay, if we know that our signal of interest is low frequency, the noise, that is distortion, other things that are actually high frequency, so we can actually do the filtering easily. And here you can see the distortion, which changes very quickly. Okay, so if I plot in the frequency domain, I can see some frequencies here and some frequencies here. So from this image, I can say that these are the low frequencies corresponding to the image, and these are further away from the middle. So these are the high frequencies corresponding to the distortion. Okay, so if I just make a filter like this, okay, what that means? 0. So if I multiply this with this, it means that I am making these frequencies 0. Okay, point by point multiplication. And after that, move back to special domain, and you can see that this is very clear. Okay. Now the question is that how to perform Fourier series or Fourier transformation. We'll discuss this. Yes.
Is this a convolution, a multiplication?
This is now this we did it in frequency domain. So this is now multiplication, and we will see that convolution in time is multiplication in frequency domain or vice versa. Okay, we will see. We'll prove this one. Okay.
So the convolution in frequency domain in time domain will be multiplication
in frequency domain. Okay. So this is a good thing about the Fourier transform. Okay. And also, as I said, the other thing is the sampling. So when we think about the sampling, we think about the impulse function, right? Because all the samples are basically an impulses, right? It's a good idea. We will define two types of impulse function. One is in time domain, one in continuous domain, and one is discrete domain. Okay, so there is a slight difference between both of them. So previously we discussed the impulse function in the discrete domain, and we said that this impulse is what? It is 1 and 0, right? Which was very clear. And whenever I multiply any signal with that impulse, I will get the signal at that point where the impulse exists. Okay. However, in the continuous domain, we can say that impulse is undefined at t equals to 0, and otherwise it's a 0. Okay. Why this is the case? Because I need this property. If I integrate delta of t, it only exists at t is equal to 0, right? So this will give me 1. If you think about the discrete version, it was 1 at t is equal to 0, but that was summation here. Discrete, we have summation. Now we have a continuous, we have integral. So for integral, what this is giving you? This is the area under the curve. However, if I just take delta of t as just, let me do it here.
How come the Theorem infinity became 1? I'm taking the area of something.
Yeah, that's the important question. That's why this definition is there. I could have said delta of t equals to 1 at t equals to 0 and 0 t not equal to 0. If I do this, what you are saying, if I integrate it, what this integration will give me? If definition is this 0, 0. So that's why this definition in continuous domain, I cannot use this definition. That definition, what it means is that the height is infinity. So it means that if I plot delta function, I can plot it in this fashion. Okay. So it means that the delta function, if that is the width, let's say this is the width of this impulse. So what will be the height? 1 over delta, right? Let's say this is the height, right? So I assume delta to be very small, nearly equal to 0. If that is nearly equal to 0, that will be infinity. Okay, if that is the case, then I can use this definition and I will get this thing. In short, what we have is the delta function is a function that has this definition in continuous domain, and it has this property. Okay, it only exists at t is equal to 0. So if I take integrate at 0, it has some value. So the area under the curve is 1. And if I multiply this delta function with any function, this will give me the value of that function at t is equal to 0, right? Similarly, if I have the shifted version, t minus t naught. Okay, so then it will be f of t naught. Okay, and this is what it is. If I just take any shifted delta function, this will give me the function value at f equals to t naught, f of t naught. Okay, what it means? This is f of t. This is a convolution, right? So if I convolve this with this one, I get that value at this point. Here, okay, good. So now for the sampling, what is important is if I want to sample here, what I get just one sample, right? At this point, if I want sampling at equal instant, I should multiply this with series of pulses, right? If I multiply this with this one, I will get the sample at different instant, right? Yes or no? Okay. So that's why I'm interested in impulse train. So what impulse train is? Just a sum of the impulses at different location. Sum of which is this. Okay. So this I call it impulse trains. with some width of delta t. So delta t is the distance between the two. Okay, and then we will discuss what is delta t. Okay, we'll discuss that. And this will give us the number of samples. The delta t will define with us that how much samples we need. Sampling frequency or sampling rate. Okay.
Is this convolution?
Up to now, no. The convolution is this. This is not a convolution. This is just some
sampling.
Yeah.
I multiply with the function.
If we multiply this with the function, then that is not the case. The case is this one. Okay, this is the and similarly, again, in the discrete domain, the data function is very simple. It's a data function 1 at x equal to 0. Okay, for the special domain, I'm using x and y for the image, right? For the image x and y, or for the 1D, it's x. Okay, so and also this makes sense there. Yes or no? If I sum this, it's only have a value at x equals to 0, which is 1. So if I put x equal to 0, okay, that has one value. Here it makes sense, but there, if I integration, I should have the area. I cannot have just one value. That's why the definition come out. Okay. Okay. So if I multiply this with again with the function, a continuous function, okay, I will get the value at x equals 0. If we have the shifted version, I get this. And make sure the continuous domain is just a theoretical way. Okay, the delta function in continuous domain does not exist because we cannot have a function that has infinity value. Okay. Okay. So if you understand this, it's just a matter of, I will say, the variables. Okay. So in a continuous domain, we have a time. Okay, like this, and in a discrete domain, we have discrete values. Okay. Now here, these are just samples. Now it depends. If I take delta x equal to 1, then you have a sample 0, 1, 2, 3, 4 like this. But if I have delta x equals to 2, which means that 0 and then 2 and then 4 like samples, I will have. Okay. So it's just a matter of the variable that I'm selecting. Yes. Okay. Fine. This we did it. Now this is a side-by-side comparison. The same thing. Only the definition here is the different than this one. Why? Because of integration and the summation. So here it's like 1. And here it's like undefined or infinity. And then definitely if you take the integration, gets 1. Here it's the summation, we'll get 1. And the same thing here, only the difference is integration and summation. Okay, clear? Now, okay, so if you understand the impulse response or impulse function, then let's move towards the Fourier transform, and then we mix together this to find out the sampling principles. Okay, so what is Fourier series, by the way? Okay, but let's say if you have this signal, so I can break down this signal in sinusoidal signals, okay? Or I can represent this signal in these sinusoidals. So basically what I have is I can sum them up in different ratio to get this. What is the difference between the Fourier series and Fourier transform? Yeah, so this Joseph Fourier actually is the one that defined this concept that any signal, but that is periodic. A periodic signal can be break down into sinusoids. Okay, so now this has, every sinusoid has different, I will say, part in this. Or okay, so I have to take these sinusoid together with the ratio that is there, and then sum them up to get this value. Okay, this is Fourier series, nothing but the signal will be break down in different sinusoids, and that will help us later on for other filtering. This is a very good example. Like we have this, I can break down in these ones. If I sum them up, I will get this. Okay, so this is Fourier series. But when you move towards the Fourier transform is for non-periodic signal. Okay, but again, the point is how to calculate these sinusoid. So the formula is this: the function f of t, which is this function, I can represent as a sum of sinusoid, with each sinusoid has its own amplitude. This formula says this, yes or no? The weight, yeah, because every sinusoid may not have the same weight, right? Because this is more, this is less, and this is less, which makes sense, right? So how to calculate this weight? The weight formula is given here, which again makes sense. Why this makes sense? Because I'm taking that signal and multiplying with that specific sinusoid, taking the integral. What this means is that I'm taking that signal and a sinusoid, try to find out how much match I have, which we call it correlation. The correlation, how much we have. So the more correlation we have, the more weight we'll have. The less correlation we'll have, the less weight we'll have. How to calculate this weight? So what I will do, I will take that signal I have, and multiply with the sinusoid and take the integral. What this will give me? This will give me the match. How much match the sinusoid will have with my signal. At a specific end will give me, for example, if I have
the weight of,
let's say my signal is sinusoid, already sinusoid. If I take another sinusoid of the same frequency and I take Cn, the Cn value will be 1 because it's a correlation. Okay. So in other words, let's keep it very simple. That this Cn gives how much correlation I have from that sinusoid to this signal. Okay, and give us the weight.
So Cn is the weight, or what's the weight?
Yeah, CNS you can call it as the weight.
So if you substitute this f of t into that, they will cancel each other.
No, don't substitute.
But what about f of t? What is f of t?
So this f of t, first we have to calculate this. This will be just a number. That number will be.
What is f of t? I need to know f of t to calculate Cn.
About what? F of t. F of t. Okay. F of t is my signal. This one. It's original signal. Okay. So once I take that signal, one time period of that signal, okay, I get a number. That number I will put it here. So I get f of t in terms of the sinusoid.
Okay. So which I think differentiate f of t prime, f of t Fourier, or I don't know. Because when I see them, I see together.
So this is actual formula is this. But with f of t, I can write a sum of sinusoid with different weights. How to calculate that weight? Using this formula. Okay. So let's say if Cn is 1, it means that sinusoid is the best one for this. Okay. So now the Fourier series is for the periodic signal. If you have non-periodic signal, the similar formula we will have but the integral should go from minus infinity to plus infinity instead of just one time period. Okay, here I just take one time period because of the repetition, right? Okay, so the Fourier, this is our concern. Okay, this is our main topic, the Fourier transform, and this is the formula for Fourier transform. Again, I take a signal, just multiply with the sinusoid I want, and take the integral. It will give me if this sinusoid exists in the signal or not. Okay, and inverse will be inverse of that. Inverse of Fourier transform. It's just like the same one with the inverse function. Yes or no? Okay.
So mu is
Frequency. Okay, so that sinusoid I can write in this fashion, right? So this now from this formula it makes sense. I am actually distributing f of t into the sinusoids. Okay, this is what I'm doing. This is Fourier transform. Nothing else. Only you have to remember the formula if the formula sheet is not given up. Okay, so now as I said, the convolution in Fourier transform is what? The question is, if I do the convolution that I did before, what it will look like into the Fourier transform? Yeah, so yeah, but we have to prove it, right? So let's say I convolve f of t with h of t. This convolution formula is this, right? We did this. Okay, now if I put this formula and take the Fourier transform of this whole, taking the Fourier transform of this, using the formula, I will take the Fourier transform of the convolution, multiply with the exponential, using the definition of Fourier transform. Okay, and what is this? Put this value here, and just rearrange them. We have t and we have d tau, right? So I can separate them, first find the t, and then after this, d tau. So what is this?
this is
Again, yeah, Fourier transform.
h of t.
H of Fourier transform. Yeah, Fourier transform of this will be h of mu, but yeah, with the shift. However, how to find it? I can do one thing. I can do change of variable. Let's say call it, let's say a. Okay, so we have a equals to t minus tau. Fine. If that is the case, then what will be t equals to a plus tau, right? Yes, and dt by d tau equals to, this will become 0 and this becomes 1. So dt equals to d tau. Okay, so if I do this change of variables, what I will get is, after solving it, h of mu e power j 2 pi mu t.
Why would you have the shift in here?
No, this is what I did. If I put these values here, what I will get? Okay, here, look it here. Okay, minus infinity to plus infinity. H of a, yes, and e power minus j 2 pi mu, and t is a plus tau and d tau. Okay, fine. So now here I can say this, h of a e power minus 2 pi mu a, right? So this is dA, and the other e power, this is just a constant, right? 2 pi mu tau. So this is what we did. I hope that you understand. It's a bit messy, but this is what we did. This becomes, this part becomes h of mu, and then multiply with this. Now if you have h of mu, which is a constant here, I put it here. This becomes this. This is what? Fourier transform of f. Okay, so what I get? It means that if I take the Fourier transform of f of t convolved with h of t, I get this. So this is just a proof of that. Yes. Okay. Okay. So let's solve some examples. As I mentioned, Fourier transform is basically for two reasons we are discussing. One is the fitting. We already saw that convolution become multiplication, so it's easy. Convolution is much more expensive than multiplication. Okay. The second thing is sampling. Okay. In order to discuss the sampling, there are a few examples that will help us understand the sampling. So first example is, if let's say you have a function which has in time domain is a constant a from minus w by 2 to w by 2, any value. Okay. So it's a box function. Okay, so let's see what's the Fourier transform is. Okay, maybe with some of your background, if you have a square function, what will be the Fourier transform of this? Sinc. Okay, so I think you guys already know. So if I put it in the Fourier transform here, this is a from minus w by 2 to w by 2. Yes. Okay. If I take the integration, okay, I get this term, and this specific term is called as a Sinc function. So I can just write in a Sinc formula. Okay, it's a sine of this over sine of theta over theta. Okay, let's say. Okay, sine of theta over theta, which is called as Sinc. Okay, so that function is this. This is Sinc function. So it's like a maximum amplitude and dying towards the edges. Okay. Now from here, this is the time domain. This is the Fourier domain, and this is vice versa. If the Sinc is in time, the box will be in frequency domain. And how to find? Let's say I give you this. You can directly find out that this is a Sinc with some width. So let's say the width goes from minus w by 2 to w by 2 with the height of a. So the zero crossings will be 1 by w, 2 by w, 3 by w, and similarly here the height will be a into w, which is the total box area. Okay. Okay. Now keep in mind that the box in time is actually a Sinc in frequency domain. Now what is the Fourier transform of impulse constant? Okay, if I want to find the Fourier transform of delta t, I take the definition of Fourier transform, and this only exists at t equal to 0. If I put t equals to 0, I get 1. Okay, which is a constant. It means that we have an impulse become constant. Similarly, if we have the impulse in Fourier domain, then what will be?
The inverse would be 1.
Constant. Okay, so this is the good thing about the Fourier transform is that it's a vice versa. Okay, similarly, if you have a shifted data, the Fourier transform of this will be exist at t equals to t naught. So I have to put t equals to t naught in this equation. What I get? An exponential minus j 2 pi mu t naught. Okay, so this is the Fourier transform. So if I just write it down, I can say that delta t is actually is 1. Okay, Fourier transform, and if I shift it, Fourier transform of this is e power j 2 pi mu t naught. Okay, so these are the transform pairs. Now keep these things in mind and we go forward. Okay, since in the sampling is multiplication of the plane of impulse with the continuous signal to get the sample, right? So now we need to find how these samples will look like in Fourier domain. Okay, so let's again start with the definition of the train impulse, which was this, right? So if I want to take the Fourier transform of this, the direct taking the Fourier transform is not possible. But one thing I know that this is periodic, right? So if this is periodic, I can take the Fourier series. Okay, so if I take the Fourier series of this impulse train, using the Fourier series formula, I have this, right? This is the Fourier series formula. I need to find Cn. What is Cn? Cn is this function. Okay, and this only exists from one time period here. Okay, so what is this function in this time period? Delta of t. Okay, and if that is the case, this only exists at t is equal to 0. If I put t equals to 0 in this, I get 1 by delta t. Put back here to find the Fourier series. So what I get? This one. So it means that in Fourier series, the impulse train is represented by this, but still we are not done because we want to find the Fourier transform of this impulse train. So let's take the Fourier transform of this. If I want to take the Fourier transform of this, I know from the table that the Fourier transform of this is equal to this, which we already did. If you remember that, we did the shifted one had what was that? E power minus j 2 pi mu t naught. Okay, so using the property, this is called the symmetric property, I can find this one. Or in other words, if I take this and find the inverse Fourier transform, I will get this. Again, see, I have an impulse train and I want to find the Fourier transform of this impulse train. But directly finding this is not possible. So what I did, I did a mathematical trick. I find first Fourier series because it's a periodic. What Fourier series give me? An alternate expression for this train. Okay. Now after that, it's easy to find the Fourier transform. So if I take the Fourier transform, the only thing I can take the Fourier transform is this one. This is just a constant, right? So if now from the Fourier transform, if I take the inverse Fourier transform of this, I get this, which is the same thing. Or I already did here. You see the Fourier transform of the shifted delta function. Okay. Now if I put this here, what I get? It means that the Fourier transform of the impulse train, which is S of u, is this. And what is this? As impulse train as well. Okay, why I'm doing this? Just wait for it. Then why I'm interested in finding it. When we want to do the sampling. Okay, so if I want to plot it, I have the impulse train. Yes, and in the Fourier, again I have the impulse train. But here we have the difference is delta of t, which is time domain, and I know that time is inverse relation to this frequency. So if this is delta t, this will be 1 by delta t, which is also from the formula. Also, I can say that this is mu minus n by delta t, means that the trains are 1 by delta t, 2 by delta t, 3 by delta t, and in the negative direction as well, right? With the amplitude of 1 by delta t.
C is bigger, here it will be smaller.
Yeah,
If this is small,
it will be bigger. And this is what we are doing next. Okay, so up to now it's clear that the pulse train in time is also pulse train in the frequency, but the relationship you are now understand. This is delta t, this is 1 over delta t, which is in frequency have an inverse, and the amplitude is 1 over delta t, right? So mathematically I can represent in time domain, and I will just go towards the frequency again. We have a continuous signal, okay, and we have a pulse train. If I multiply this, I will get samples, right? And mathematically I can write f of t multiplied with pulse train, and this pulse train I can write as this. Yes, this is this function. Okay. And this is just pictorial view of doing this, but actually what you get the points, the sample points like this one. This is the actual thing that we'll get after sampling. Yes. Okay. And also I can write that this is again from the first few slides. F of t multiplied with the delta function will give me that point, right? K delta t. This is again the property of delta function. This is the property of delta function. Nothing else. Okay. Now what I'm trying to do is this is time domain where I multiply these two. Fine. In the time domain I multiply pulse train with the signal. So in frequency domain what I'm doing, convolve the pulse train with the Fourier transform of this. Yes. Okay. So if that is clear, and this is what we said, convolution is multiplication or multiplication. Okay. So if that is the case, this is the sampled version, right? This is the sampled version. If I take the Fourier transform of this, it means that these are the multiplication. So this becomes convolution in frequency domain. If this becomes convolution in frequency domain, I can write as the convolution formula. And what is S of u minus t, which we derived it before? Okay. This is basically this function. This we derived it here. Here, okay, S of u was this. So S of u minus tau will be u minus tau this. Yes or no? If I just put these values here, okay, I get this value. The summation I can move, and where this thing will exist only where tau is equal to mu minus n by delta t. So if the whole function exists only at tau equals to mu minus n by delta t, so this becomes this. Yes or no? Now it means that if I take the Fourier transform of the sample signal, I get this thing. And what this means? It means that what is f of mu? F of mu was the Fourier transform of f of t. So it means that if I take the Fourier transform of the sampled signal, I get the various copies of the Fourier transform of f of t. Still, if you're confused, okay, let's see this. You have a signal, okay? So we have continuous signal, I multiply with this to get the samples. This is in time domain. The same thing I want to visualize in frequency domain. So let's say the Fourier transform of this is this, and then the Fourier transform, we already proved it, is this. Here I'm multiplying, here I should convolve. If I convolve these two, I get this, which we already proved it here, that if I take the Fourier transform of the sampled signal, I get the multiple copies, which I get it, right? So I get what? Multiple copies. Yes or no? Now, if that is clear, from here I can find out what should be the sampling rate. Sampling frequency, what will be the sampling frequency? So from here I can say that the sampling frequency should be twice of the maximum frequency. This is, let's say, f max, okay? So this should be twice of f max, right?
Okay.
And f max then should be equal to what? Delta. What is sampling frequency? Sampling frequency is 1 over delta t, right? Okay. I want this distance to be greater than or equal to twice of f max in order to get the proper sampling.
Why twice?
If not twice, what will happen? If this distance is less than this, how will be the shape of this?
Will be small.
Okay, so yeah, this is next slide. Let me show you. If 1 by delta t, which is sampling frequency, if this is greater than f max, this is f max, huh? Greater than f max, I get this shape. Okay, if that is equal to f max, I get this shape.
Exactly.
And if it is less than f max, I get this shape. Okay.
So there will be some losses here in the second figure, right?
In the second figure, it's very
No, I mean,
critical.
the last and the second one. Not the left.
The second
Less than and
more than is okay. Okay, this is also somehow okay, but you have to be very careful. And this is definitely here will be low. This is what I want to say. Okay, now why is this important? If I want to sample a signal, after sampling, I want to reproduce the signal. So if that is the case, it's very easy. What I can do is I can take this part inwards Fourier transform. What I will get? This thing. But if I take this one, I will never get that signal, but some distorted signal.
okay.
Let's say I have the sound. So I sampled it, processed it. After that, I want to listen sound. I have to do this thing to get back the continuous wave. Otherwise, I will not be able to listen sound clearly. Okay. I am basically convolving this frame with this one. As I convolve, I will get this thing. The reconvolution is what? If we shift it, it will get the same. Or shift this one, get the same. And shift and then sliding. So I get this thing. Okay. So that's why we have the 1 by delta t comes up from the pulse rate. So now you understand that why the sampling is twice of the maximum frequency. Okay. So now in order to get back the signal, as I mentioned, I need to have the filter multiply with this. Okay, and I will get back the original signal, this spectrum which was the original, and then I take the inverse Fourier transform to get back the signal. Up to now, I'm just doing signal processing. I did not even discuss the images, right? And because the amplitude was 1 over delta t, so amplitude of this should be what to get back? It should be delta t. Okay, so this is the filter delta t going from u max or mu max to mu max. What is mu max? This is this one. And once I do this, I get this. This is the original spectrum. Just a quick recap. You see all these derivation, I did it just to give you insight that why the sampling frequency is twice of the maximum frequency, or why we use the Nyquist, or what will be the sampling frequency. This is the answer for all these mathematics. Okay. So what I did, in the time domain, I have this, the signal multiplied with pulses to get the sample version. Right. So I want to see the same thing in frequency domain. Okay. Then what will be the same thing in frequency domain? So assuming that this signal has a Fourier transform of this, and we already proved before that this pulse train is also a pulse train in a frequency domain. And here we are multiplying, so here we are doing convolution. So results of multiplication become this, results of the convolution become this thing. Agree or not?
Yes.
Okay. If we get this thing, okay, it means that the sampled version, this has frequency transform of this, has frequency transform of this, and the sampled version has a frequency transform of this. So if I have the sampled version which has the frequency transform of this, if I want to recover the original one, I will just take this part, which is the frequency transform of the original signal, and go back inwards to get back the original signal. If that case is not there, the Fourier transform is not there, there's no way to recover it. So this is the power of Fourier transform. How to get this? I will just multiply with a filter, simple filter. So this is what I did. I just took this one, multiply with this filter to get this, and then take the inverse to get the original signal back. So just to finish this one, since we are doing time domain and frequency domain side by side, right? So if I'm doing this filtering in frequency domain, what will it be look like in time domain? So here, what I did, I multiplied the sampled signal in frequency domain with the filter. Multiply, right? So in time domain, what I'm doing, convolving this signal with this. What is this signal in time domain? A sampled version. What is that signal in time domain? A Sinc, which we already derived. That's why we derived it, right? So it means that if I convolve the sample signal with inverse Fourier transform of the box filter, I get something like this. And this is somehow call it like in time domain we do interpolation. So this is a formula for interpolation, but anyhow you don't need to go in detail, but this is how it look like. Okay. So what I'm doing is I'm doing like every operation in time and frequency just to make sense of it. So again, the question is, if we don't do the Nyquist, if we do the less than Nyquist frequency, we get what? Aliasing. What is aliasing? A false identity. Okay, so what do we mean by a false identity? Let's say you have a sinusoid and I sample it like some pattern, another sinusoid, and I sample it, let's say as I did this, okay, lower than, if I sample this signal lower than the Nyquist, you see the both samples are similar. So it means that this has a different frequency, right? This has a different frequency. However, because I did not sample it right, I get the same sample for these two. This is called aliasing. If I go convert this back to the original signal, both signal will result this thing. Even I have this signal, but I did not sample it according to the Nyquist. Therefore, if I go back, I will get this signal instead of that signal. So this is called aliasing, the false identity.